Welcome to Lecture 4. In this lecture, we will learn about the inverse of a matrix. We'll define this concept and then also show a very easy way to calculate the inverse. This idea is very simple. Let me give you an example. Suppose that you had the equation 3x is equal to 12. Well, it's very easy to solve this problem. What we would do is multiply each side of this equation by 1/3. In this way. And then on the left-hand side, 1/3 times 3 is equal to 1, and 1 times x is simply equal to x. And on the right-hand side, 1/3 of 12 is 4. And we're all done. Now we have solved the equation. Now this number 1/3 here is, we chose that because when we multiply the left-hand side by 1/3, we get a coefficient of 1. That number 1/3 is said to be the multiplicative inverse of the number 3, and that's what we will always do. For instance, if we, as another example, if we had 7x is equal to 28, then of course what we would do there is multiply both sides by 1/7, because 1/7 is the multiplicative inverse of 7, and when we multiply the left-hand side by 1/7, then again we're going to get a 1 times x, which would give us x on the left-hand side, and on the right-hand side we would get 1/7 of 28, which is 4. So this idea of multiplying both sides of the equation by the multiplicative inverse of the coefficient of the in the unknown term, this might raise a question in your mind, because after all, as we have seen already, so the question is this. I'll say, can we do something similar with matrices? And let's be more specific now. Let me explain exactly what I mean. Let's go back for a moment to Lecture 2. And in Lecture 2, we had this system of equations here. And we said that that system of equations is equivalent to the following matrix equation. This implies that AX equals B, where, maybe I should say instead of X, since we already have one of the unknowns is called X, I don't want to use X for a vector as well. I'll say V. So this system of equations implies AV is equal to B, where A is equal to 1, 1, 1, 2, -1, 1, 3, 1, -1. V is equal to X, Y, Z, and B is equal to 6, 3, 2. And and we've already discussed that the equivalence of this matrix equation with this system of equations. We've already discussed that in lecture 2. But if you look at this matrix equation right here, and keep in mind now that A is a known matrix and B is a known vector, V is the unknown. It has the unknown components x, y, and z. So we have a known quantity, an unknown quantity, and a known quantity. And you look at that, and that looks just like these two equations. We have a known quantity, an unknown quantity, and a known quantity. Or here, known, unknown, known. So this matrix equation has exactly the same form as these scalar equations that we have at the beginning of today's lecture. And so it leads to the question, is there some matrix, and we'll call it a to the negative 1 power, just like 1/3 is 3 to the negative 1 power, 1/7 is 7 to the negative 1 power. So in keeping with that kind of notation, we're going to give this matrix that we're looking for the symbol of a to the negative 1, and we'll call it A inverse. And so the question is there some matrix a to the negative 1, or A inverse, such that A inverse A V equals V? We want to find a matrix so that when we multiply the left-hand side by that matrix, then we'll just get V alone. Just like up here when we multiplied the left-hand side by 1/3, then the 1/3 and the 3 gave us 1, and 1 times x is x. So we got x alone. Or here we had 7x, so we multiply by 1/7, and when we do that again, we get x alone. So we want to find some matrix that we could multiply by on the left-hand side such that A inverse, we'll call it A inverse times A times V would just give us V alone. And then, of course, we would multiply the right-hand side by that same matrix, and after doing the calculations, then we should have our answer immediately. So that's the question. And the answer in this case, and in fact, in any case where the system of equations has a unique answer, such a matrix will indeed exist. And so now we ask, how can we find it? Okay, now before I show you how to find this, and it's very easy, but I want to introduce a little terminology that we haven't discussed before, and that is the identity matrix. The identity matrix, you have to know what order you're talking about, but the 2x2 identity matrix is that. The 3x3 identity matrix is this. And so on. The identity matrix is just a matrix that's equal to 0 everywhere except along the diagonal, and all the diagonal entries are equal to 1. And the thing that's special about the identity matrix is that notice that if you take the identity matrix, let's take the 2x2 case, if we take the identity matrix and multiply it by any vector, let's see what we'll get. Well, 1, 0, 0, 1 times A, B, and the first entry will be 1 times A plus 0 times B, so we'll get A. The second entry will be 0 times A plus 1 times B, and it will give us B. So the identity matrix times AB is equal to AB. And similarly, you could calculate that if you took the identity matrix, the 3 by 3 identity matrix, and you multiplied it by A, B, C, you would get A, B, C. And so it's acting like the number 1 does. You know, up here we picked 1/3 because 1/3 times 3 will give us 1, and then 1 times x is x. We picked 1/7 here because 1/7 times 7 will give us 1, and 1 times x is x. So the idea here is that we want to find this A inverse so that A inverse times A will give us the matrix equivalent of the number 1. And that matrix equivalent of the number 1 is the identity matrix. So we want A inverse times A. We want A inverse A to be equal to the identity matrix, because then, coming back up here to this equation, if A inverse A is equal to the identity matrix, well, we know that the identity matrix times V will indeed give us V. So, how do we find A inverse? Okay, and this is called the Gauss-Jordan technique. And it goes as follows, okay? Again, let's remind ourselves, the matrix for which we want to find the inverse is A, where A is 1, 1, 1, 2, negative 1, 1, and 3, 1, negative 1. Now, the Gauss-Jordan technique goes as follows. We write down the matrix that we want to invert. And then we will draw a vertical line as though we're going to have now an augmented matrix. But on the right-hand side, instead of putting some... and as I said, on the right-hand side, and I want to be a little more specific, to the right of that vertical line, instead of putting the right-hand side of some equation, what we will put is the identity matrix. So we'll have 1, 0, 0, and since this is a 3 by 3 case, we'll have 1, 0, 0, 0, 1, 0, 0, 0, 1. And now what we will do is, by using only the procedures that we talked about already with Gaussian elimination, what we want to do is work on this until the matrix on the left-hand side, that is to the left of the vertical line, we want to get the identity matrix over here. And once we get the identity matrix over here, then whatever is over here will be the inverse of A. So let's see how this will go. Okay? Well, we're going to go through the first steps of Gaussian elimination in exactly the way we have before. So we'll write down this first row, 1, 1, 1, 1, 0, 0. And now here's our main diagonal, 1, negative 1, negative 1, and we have, as we've seen before, these three numbers below these are the non-zero terms below the main diagonal. So we want to zero those out. And we know that we can do that. We can get rid of this 2 by adding negative 2 times the first row to the second row. So let's do that. Negative 2 times 1 is negative 2, and 2 gives 0. Negative 2 times this 1 is negative 2, and negative 1 gives negative 3. Negative 2 times this 1 is negative 2, and 1 is negative 1. Negative 2 times this 1 is negative 2, and 0 gives negative 2. Negative 2 times 0 is 0, plus 1 is 1. Negative 2 times 0 is 0, and 0 plus 0 is 0. Now to get rid of the 3 here, we add negative 3 times the first row to the third row. So negative 3 times 1 is negative 3, and 3 gives 0. Negative 3 times this 1 is negative 3, and 1 gives negative 2. Negative 3 times this 1 is negative 3, and negative 1 is negative 4. Negative 3 times 1 is negative 3, and 0 is negative 3. Negative 3 times 0 is 0, and 0 is 0. And negative 3 times 0 is 0, plus 1 is 1. So now we have eliminated 2 of the original 3 non-zero terms below the main diagonal, and we have only 1 left, and that's this negative 2. And so, as I have discussed before, I would rather avoid fractions. And so what I will do next is I will multiply the second row by 2 and the last row by negative 3. So we'll get 1, 1, 1, 1, 0, 0. And then, as I said, we'll multiply the second row by 2. So we get 0, negative 6, negative 2, negative 4, 2, 0. And then multiply the bottom row by negative 3. So we get 0, 6, 12, 9, 0, negative 3. And so now we're ready to add the second row to the third row to get rid of this last non-zero term below the main diagonal. And so we will have 1, 1, 1, 1, 0, 0. And 0, negative 6, negative 2, negative 4, 2, 0. And now we add the second row to the third row. 0 plus 0 is 0. Negative 6 and 6 is 0. Negative 2 and 12 is 10. Negative 4 and 9 is 5. 2 and 0 is 2. 0 and negative 3 is negative 3. So now, at this point, you could say that we're halfway done, because we have eliminated, remember again, our goal is to get the identity matrix here on the left hand, in the left part of this big matrix. And we have now eliminated all the non-zero terms below the main diagonal. Now what we want to do is to eliminate all the non-zero terms above the main diagonal. So now what we do is really just the reverse of what we've just done. And we so far in all of our work previously and in this problem that we're doing here, we've been eliminating zeros below the diagonal by moving from top to bottom and left to right. Now we want to eliminate non-zero terms above the main diagonal by moving from bottom to top and right to left. So, for instance, you see here there are 3 terms above the main diagonal the 1, 1, and negative 2 here, there are 3 non-zero terms above the main diagonal, and we would like to eliminate those. And just as we usually start in the upper left-hand corner, now we start in the lower right-hand corner. We want to add multiples of this 10 up above, first to get rid of the negative 2, then to get rid of the 1, and then we'll add multiples of the second row to the first row to get rid of that remaining 1. Okay, so if you still want to, now at some point we're probably going to have to go ahead and introduce some fractions, but I'm going to hold out just as long as I can on that. So let's say we have the 10 down here, and so what I will do next is I'll multiply the top row by 10 and the second row by 5. So I'm going to have 10, 10, 10, and if you don't like to do it this way, that's fine. You do it whatever way you feel most comfortable with. But again, I would just prefer to avoid the fractions as long as possible. So if I multiply the top row by 10, that's what I'll get. And now, as I said, I'll multiply the second row by 5. So we get 0, negative 30, negative 10, negative 20, and 10, and 0. And the final row I'll just leave as it is, 0, 0, 10, 5, 2, negative 3. And you can see now why I chose to multiply the top row by 10 and the second row by 5, because it gave us a 10 and negative 10 here, so it's going to be easy for me to eliminate those by adding the third row up above. So now I'm going to go ahead and do that. I'm going to add the third row to the second row to get rid of this negative 10, and then I'll add the negative of the third row to the first row to get rid of this positive 10. So let's see what happens when we do that. Okay. So in the spirit of doing everything backwards, let me go ahead and write the last row. So we have 0, 0, 10, 5, 2, negative 3. Just think of all of this as being the backwards process of what we've done already. Now we're going to add the last row to the second row in order to get rid of this negative 10. So when we add 0 to 0, we get 0. When we add 0 to negative 30, we get negative 30. When we add 10 to negative 10, we get 0. When we add 5 to negative 20, we get negative 15. When we add 2 to 10, we get 12. And when we add negative 3 to 0, we get negative 3. And now we'll add the negative of the last row to the first row to get rid of this 10. So negative 0 plus 10 is 10. Negative 0 plus 10 is, again, 10. Negative 10 plus 10 is 0. Negative 5 plus 10 is 5. Negative 2 plus 0 is negative 2. And the negative of negative 3 is positive 3 plus 0 is positive 3. And now you can see that on the left-hand side, or to the left of the vertical bar, we're getting very close now. We only have one more term here that needs to be eliminated. And so I guess I might as well go ahead one more time to avoid fractions. I will multiply the top row by 3. So we'll get 30, 30, 0, 15, negative 6, 9, and then everything else I'll leave as it is. So 0, negative 30, 0, negative 15, 12, negative 3, 0, 0, 10, 5, 2, negative 3. And now we will add the second row to the first row to get rid of this 30 here. And so we'll be left with the following: 0, 0, 10, 5, 2, 3, 0, negative 30, 0, negative 15, 12, negative 3, and then finally, when we add the second row up to the first row, 0 plus 30 is 30, negative 30 plus 30 is 0, 0 plus 0 is 0, negative 15 and 15 is 0, 12 and negative 6 is 6, and negative 3 and 9 is 6. And now the last thing we do, recall that our goal was to get the identity matrix here to the left of the vertical line, and that's easy to do. All we need to do now is multiply through the first row by 1 over 30, the second row by 1 over negative 30, and the last row by 1 over 10. And so when we do that, we will get 1, 0, 0, 0, 1, 0, 0, 0, 1. And on the right, we will get 0, and then 6 divided by 30 is 1/5. 6 divided by 30 again, 1/5. Negative 15 divided by negative 30 is 1/2. 12 divided by negative 30 will be negative 12 over 30. And if we divide top and bottom by 2, that would be negative 6 over 15, or let's see, negative 2/5. So negative 2/5 there, and then the negative 3 divided by negative 30 will be 1/10. And finally, for the last row, we have divided through by 10, so we get 5 over 10, which is 1/2, 2 over 10, which is 1/5, and 3 over 10, which is 3/10. And that is the end of the procedure. We have now obtained the identity matrix to the left of the vertical line, and so the claim is that this matrix right here on the right hand to the right of the vertical line, this is the inverse of the matrix A that we started with. So I'll say we claim that A inverse is equal to 0, 1/5, 1/5, 1/2, minus 2/5, 1/10, 1/2, 1/5, and 3/10. We claim that that is A inverse. And how do we check it? Well, checking it is very easy. We just take that matrix and multiply it by our original matrix A and see if we really do get A inverse. So A inverse times A would be 0, 1/5, 1/5, 1/2, negative 2/5, 1/10, 1/2, 1/5, 3/10. And then A is 1, 1, 1, 1, 1, 1, 2, negative 1, 1, and 3, 1, negative 1. And let's see if this will work. Okay, so when we go across the first row and down this first column, we'll have 0 times 1 is 0, and then 2/5 and 3/5, and 0 plus 2/5 plus 3/5 is equal to 1. When we go across this row and down the middle column, we will get 0 minus 1/5 plus 1/5, and that's 0. And now when we go across this row and down the third column, we get 0 plus 1/5 minus 1/5, and that is 0. Now, let's look at the next row. When we go across this row and down this column, okay, we're going to get 1/2 minus 4/5 plus 3/10. So let's think about that. 1/2 is the same thing as 5/10. So we're going to get a 5/10 there, and then we get 3/10 from the 1/10 times 3. So we have 5/10 and 3/10. That's 8/10, which is the same thing as 4/5. And then from the negative 2/5 times 2, we get a negative 4/5. So when we add those together, we do indeed get 0. Now, when we multiply the second row times the second column, we will get 1/2, and then the minus 1 times minus 2/5 will give us plus 2/5, and then 1/10 times 1 will give us 1/10. So we just add up 1/2 and positive 2/5 and positive 1/10. Well, 1/2 is 5/10. 2/5 is 4/10, so 5/10 and 4/10 is 9/10, and 1/10 is indeed 1. And then finally, when we take the second row times this third column, we'll have 1/2, which is 4/10. 5/10, of course. So 1/2 times 1 will give us 5/10, minus 2/5, which is minus 4/10. So 5/10 minus 4/10, that's 1/10, and then a negative 1/10, so we get 0. Now for the final row, 1/2 times 1 is 1/2, and 2/5. Okay, 1/2 is the same thing as 5/10. 2/5 is 4/10. So we have 9/10, and let's see here. Oops, it looks like we have an error somewhere. Let me stop the video for just a moment and find out where this error is. Okay, well, that didn't take long. Notice if we come back up here in the procedure that we were following to derive the inverse, if you go from here, from this step right here to this step, you'll notice that the negative sign on the 3 was accidentally dropped in going from here to here. So we need to put that negative 3 in, and then make sure, remember the last step just consisted of dividing the first row by 30, the second row by negative 30, and the last row by 10. So that means that the only change that will make in this final result is that we'll have a negative sign there, and likewise then an A inverse. Now we'll have a negative 3/10. So let's put this down here. And of course, that's not going to change anything that we've done so far. So we're still in good shape. Okay, so now we're ready to calculate this third row. So 1/2 times 1 is 5/10, and then 2/5 is 4/10. So we have 5/10 and 4/10, that's 9/10. And then minus 3/10 times 3 is minus 9/10, so we get 0. 1/2 times 1 will give us 5/10, minus 1/5 times 1 will be minus 2/10, so that's 3/10, and then minus 3/10 times 1 is minus 3/10, and 3/10 minus 3/10 is 0. And then finally, 1/2 times 1 plus 1/5 times 1, and then minus 3/10 times minus 1. So we'll have 1/2 and 1/5 and a positive 3/10. And let's see what that will give us. 5/10 is, excuse me, 1/2 is 5/10, and this is 2/10, so that's 7/10 plus 3/10, and sure enough, we get the answer of 1. And so on the right-hand side, we are indeed getting the identity matrix, and therefore this expression right here is the correct expression for A inverse. And that's how the Gauss-Jordan method works. That's how, so if you were given a matrix, you can find its inverse using this Gauss-Jordan method. And again, all you need to do, you take the matrix for which you want to find the inverse, put it on the left part. On the right, you put the identity matrix, and then work doing Gauss elimination forward first in the usual way, and then backwards, until finally you arrive at the identity matrix on the left, and whatever is on the right will be the inverse of your original matrix. And we can finish this up now by seeing how we would use that for our system of equations. Remember, okay, we had AV is equal to B, where this is A, this is V, and this is B. Okay, I'll just copy all of this. And we'll see how we can use the work we've just done. So if we come down here and paste it, okay. So here you see our system of equations one more time, and we noted that that was the same as AV is equal to B. But now the important thing is that we now have calculated A inverse. So let's do the following. We take this equation, AV equals B. Okay? And now we can symbolically do this as follows. We'll multiply both sides by A inverse. So A inverse AV equals A inverse B. But on the left-hand side, A inverse A is the identity matrix times V is equal to A inverse B. And of course, the identity matrix times anything is just that thing itself. So we get V is equal to A inverse B. And now we substitute in. This says X. V is the vector X, Y, Z. You see that we're solving for all of the unknowns at once. So X, Y, Z is equal to A inverse times B. All you have to do now is a matrix multiplication. You take the matrix A inverse, which is 0, 0, 1/5, 1/5, 1/2, negative 2/5, 1/10, and then 1/2, 1/5, negative 3/10. That's the matrix A inverse. B is 6, 3, 2. And now all we have to do is carry out the matrix multiplication on the right-hand side, and we will get X, Y, and Z. So let's see what happens. When we multiply the first row times this, we'll get 0 plus 3/5 plus 2/5, and that is 1. When we multiply the second row times this column, let's see, we're going to get 6/2, which is 3. And then we'll have 3 times negative 2/5, so we're going to get negative 6/5, and finally 2/10. So let's just write that down up here. We have 6 times 1/2, so that was 3. And then minus 2/5 times 3 is minus 6/5. And 1/10 times 2 is 2/10, or this is the same thing as 1/5. Well, negative 6/5 and 1/5 is negative 5/5, so this is the same thing as 3 minus 5/5, or 3 minus 1, or 2. So our entry here is 2. And then for the multiplication of this last row times this column vector, we get 1/2 times 6. Might as well go ahead and use our scratch space again. So 1/2 times 6 will be 3. Plus 1/5 times 3, that's plus 3/5. And then finally, minus 3/10 times 2, which is the same thing as minus 6/10 or minus 3/5. And of course, 3 plus 3/5 minus 3/5 is just 3. So we end up with the answer that x, y, z is equal to 1, 2, 3. And of course, if we look back now at lecture 2 and remind ourselves, remember in lecture 2 we solved this system of equations by Gauss elimination, and our final result was indeed x equals 1, y equals 2, and z equals 3. But here in lecture 4, you see x equals 1, y equals 2, and z equals 3. We're getting this exactly the same answer, but in quite a different way. And it is through the calculation of the inverse. And you might wonder, well, why would I want to do it this way? Suppose that you had to solve this equation, AV equals B. Suppose you had to solve this for many different values of B. Well, if you took the Gauss elimination approach every time, you'd have to go through that whole procedure every time to calculate your answer. But if you use this inverse matrix approach, then for every B, you just have to do the matrix multiplication, this final step, because you already have A inverse, and to get your answer, you just have to have A inverse B. So for every new B, you just plug it in, do the matrix multiplication, and you're done. So that would be an example of a situation where this method would be more efficient. But if you only have to solve an equation one time, it's probably more efficient just to go straight Gauss elimination. But definitely you want to know this method for finding you want to understand the idea of an inverse of a matrix, and you want to know this Gauss-Jordan method for calculating the inverse. And as I said before, in another circumstance, I understand that a lot of these things with linear algebra you can probably do with your calculators, but you want to make sure you understand the procedures, because it will be important for you in tests to know not just how to get an answer, but in some cases it will be important to know the procedure as well. So that's all of the material that we want to cover for this lecture. And now let's consider some problems. Okay, so for the first problem in this lecture, let's do problem 7.8.3. For the second one, do 7.8.5. And then for the third one will be in class. And one final thing I want to point out is, please understand that I'm trying to avoid giving you just an overwhelming amount of homework. So I'm keeping these problems on the minimal side. But if you feel shaky about anything, you need to ask in class, and you need to practice more at home. So don't feel like these problems that I'm giving are the maximum you should do. They are the minimum you should do. And if you feel any hesitation at all about your ability, do others to get more practice. So that concludes lecture 4, and good luck.